Hello, good morning students. Welcome to the physics class. Yesterday we studied the concepts of equipotential surfaces and potential surface properties and about the potential energies. Okay, potential energy of system of 2-point charges in the absence of electric field and in the presence of electric field, and potential energy for a 3-point charges system. Okay, and the relationship between the electric field and electric potential we derived, and we discussed the concepts about potential gradient also. Okay, today we are going to learn about the electric potential energy due to a dipole placed in a uniform electric field. Yeah, let's look at the question. Electric potential energy due to a dipole placed in a uniform electric field. We already discussed the case about the dipole placed in a uniform electric field and it experiences a torque. Tau is equal to P sin theta. That concept we derived in the first chapter. Okay, now you can see in a picture the same diagram. It is the electric field lines which are marked in a red lines. Okay, those are the uniform electric field which are parallel to each other. Okay, and here is the dipole. We place it the dipole. The dipole is having two equal and opposite charges separated with a distance, that is we know that 2a. Okay, and the angle between the dipole moment, as we know that the dipole moment P is directed from negative charge to positive charge, and it is directed from negative to positive. The angle between this dipole moment and the electric field direction is theta. Okay, and hence it experiences a torque also here. So two equal and opposite forces makes the dipole to rotate in a electric field. Okay, you can see here the vertical dotted line here that shows the zero potential energy position. Okay, we discuss it later how it is called as zero potential energy and all. After the derivation, after the solution, you will come to know that. Okay, yeah. Now first look at the definition of the electric potential energy. Electric potential energy of an electric dipole is the work done in rotating the dipole from zero energy position to the desired position in the electric field. Okay, initially from zero energy position means from vertical position here. From here it will start and it may end at any other angle. Okay, so for this rotation the work done is required. Correct? The work done can be called as a electric potential energy. To derive this concept, we have to go through the torque expression. Okay, torque acting on the electric dipole in external electric field. We know this, tau is equal to P sin theta. This is the concept we already derived. Okay, and this torque rotates the dipole. And the small work done in rotating the dipole through an angle d theta without acceleration is given by, it's like we are finding the work done for the small rotation in the dipole. So small work done we can call. Right? The small work done in rotating the dipole through an angle d theta without acceleration is dw is equal to tau d theta, because from the formula w is equal to F into S, and here it is a torque is a rotating effect, hence we are using tau. For the rotating effect the displacement will be d theta, we call it as an angular displacement. Right? So W is equal to force into displacement. To that concept we can write this dW is equal to tau into d theta, and we know that the tau value here, substitute that P is sin theta d theta. Okay, so this is the small work done. So now we have to find the total work done. The total work done in rotating the dipole from theta 1 to theta 2. Theta 1 means the initial position, theta 2 means the final position where the dipole stops, right? So we have to find the total work done. First we have to find the small work done. By integrating this we will get the total work done. Yeah, look at the next step. The total work done W is the integration of the previous step, that is dW. We are integrating from initial angle to final angle theta 2. The dW value from the last equation, P sin theta d theta, and here the PE taken outside, we are integrating sin theta. The integration of sin theta is minus cos theta, and the limit varies from lower limit to upper limit, that is theta 1 to theta 2. Okay, we have to keep it as it is. And now we have to apply this upper limit minus the lower limit concept. Okay, take the minus here. First you substitute in the place of theta 2 the upper limit cos theta 2 minus the lower limit theta 1, cos theta 2 minus cos theta 1. This is the method of applying the limits. First upper limit minus the lower limit we have to substitute in the variable. Okay, now the w is equal to p cos theta 1 minus cos theta 2. This we can write by multiplying the negative sign to inside, minus cos theta 2, and this will become plus cos theta 1. So I am interchanging the term. We can write p cos theta 1 minus cos theta 2. So this work done is stored in the dipole as a potential energy. Okay, according to the electric potential energy definition, it is the work done, right? So this work done can be called as a potential energy. So we are replacing the symbol W by U, that is equal to PE cos theta 1 cos theta 2. U is nothing but potential energy. Now let's discuss the case. If initially the dipole is oriented perpendicular to the direction of E, means if we imagine that initially the dipole is aligned vertically, exactly vertical to the electric field, means you observe the zero energy position, right? So there if we place the dipole, then theta 1 becomes 90 degree. That is a initial angle, vertically, exactly vertical like this, right? And then brought to an angle theta because of the electric field lines of forces, the dipole rotates. Okay, let the final angle be theta. Then the potential energy of the dipole will be, now substitute here, the initial angle is 90, final angle is just theta. I am taking theta 2 as a theta. Then cos 90 becomes 0. Then we are getting here cos theta. So the final formula for the potential energy we can give as a U is equal to minus PE cos theta. This is the case when the dipole stands exactly vertical, okay, exactly vertical initially, and it may rotate with any other angle and it may stop with any other angle finally. Then we can use this formula. Okay, if the initial angle is not 90 degree, then we should use this formula. If initial angle is 90 degree, then we can use this formula. Okay, U is equal to minus PE cos theta. By using this concept, by using this equation, we can now predict that when the dipole energy is maximum, the electric potential energy in the dipole is maximum, minimum and 0. Okay, and when the position becomes stable or unstable, okay, that also we can discuss. Now by using the previous equation, U is equal to minus PE cos theta, the case ones, the special cases we are discussing here. The case 1, observe the case 1, position of stable equilibrium. When the dipole is said to be in stable equilibrium, when the P is parallel to E, when the dipole moment is parallel to E, means exactly horizontal, when the dipole is placed exactly along the direction of electric field, okay, then theta is 0 degree, right? Theta becomes 0. Then if you substitute cos 0 in the previous formula, U is equal to minus PE cos theta. If you substitute 0, cos 0 is 1, then you will get U is equal to minus PE. So since there is a negative, it takes a negative value, means it is the minimum potential energy. Okay, when the dipole is in the direction, the dipole moment is in the direction or in the parallel to the electric field, then theta becomes 0, then it occurs minimum potential energy. In this position, dipole will be in the stable equilibrium, means it doesn't experiences any forces. Okay, stable equilibrium, it never rotate. Okay, yes. And look at the case 2. So in the case 2, we call it as a position of unstable equilibrium. When the P is anti-parallel to the E, okay, anti-parallel means exactly opposite. The electric field direction is like this. Okay, this is the electric field direction, but the dipole moment direction is going exactly opposite to this. Okay, then we call it as an anti-parallel. So then the angle becomes 180 degree. Okay, the angle in the anti-parallel case is 180, cos 180 is minus 1. So from the formula, U is equal to minus PE cos theta becomes minus 1, minus into minus become plus. So what you understood from this, when the dipole moment is anti-parallel to E, means exactly opposite to the electric field, then the potential energy is maximum. So it is the maximum potential energy. And in this position, the dipole will be in unstable equilibrium. Unstable means it keep continues to rotate. Okay, it keep rotating in a the dipole is keep rotating in a electric field. So this is the meaning of unstable equilibrium. Stable equilibrium means the dipole never experiences any force and it never rotates. Okay, but here it keep rotating because of this maximum effect. Okay, and what if the P is perpendicular to E? Means I shown there the dotted line in the picture. See once again. So the dotted vertical line we call as a zero potential energy. If we place this dipole exactly vertical, then theta becomes 90 degree, right? Then what is a cos 90? Cos 90 is 0. Then the total potential energy becomes 0. Hence we are calling it as a zero potential energy position. So the potential energy becomes 0 when P is perpendicular to E. Theta is 90. In this position, potential energy of the dipole is 0. Understood? We discussed the three cases of stable equilibrium and unstable equilibrium and the zero potential energy position of the dipole. Okay. Now the next concept is behavior of conductors in electrostatic fields. Okay. When you place an external conductor inside the electric field, what are the changes we can observe inside the conductor? Okay, and how the electric field induced in it? What are the behaviors of that conductors relevant to the field and the charges and all that we are going to discuss now. Okay, and these concepts are very important to understand the next phenomenons. Look at the first one. The first one is the net electric field is 0 in the interior of a conductor when placed in the electrostatic field. Okay, so in the interior of a conductor, the net electric field is 0 when placed in the electrostatic field. We created the electric field. The electric field here you can see one is a positive plate and another is a negatively charged plate, and these are the field lines. As per our knowledge of the electric field lines start from the positive and ends at the negative. It moves towards the negative, right? So the directions are like this. Okay, this is a E external electric field directed from positive plate to negative plate. You can observe. And we placed the conductor here. On conductor plate we placed. Okay, when you place the conductor plate, the conductor is having both negative and positive charges. Because of the attraction, observe, towards the positive plate, the negative charges in the conductor get attracted to one side, right? Because there is a positive and negative attractions. And again at this another side, because of again attractive property, for the negative charged plate, the positive charges inside the conductors get attracted and it accumulated at another end. Okay, so you can observe here, towards the negative charged plate the positive charge alignments are there, and towards positive charged plate there are negative charge alignments. Okay, now observe the direction of the electric field inside the conductor, right? Inside the conductor, the electric field started from positive charge and it moved towards the negative charge. You can observe, which are exactly opposite to the external field. These are the external field. The directions are opposite to it. Okay, so we can say that here the electric field induced inside the conductor and electric field at the external both are equal in magnitude but opposite in direction. Therefore, the net electric field becomes 0. Okay, it get cancelled each other. Hence, you will get electric field as a 0. Means electric field is 0 inside the conductor when you place the conductor in external field. And look at the next second property. The net charge at any point inside the conductor is 0. The net charge at any point inside the conductor is 0 and any excess charge resides at its surface. Okay, so this is also a property of charge, right? A neutral conductor has equal amounts of positive and negative charges, right? That is, we know a neutral conductor, neutral body has an equal amount of positive and negative charges. When the conductor gets charged, the excess charges always resides only on the surface. So here, charges always resides on the surface of the conductor. You can see in a picture, okay? Whatever the shape of the body, charges always resides on the surface. Hence, inside the conductor, there are no charges. Hence, no electric field. This is the second property. Okay, second behavior of a conductor. Yeah, next, third property, the very most important. Okay, the electric potential is constant at any point inside and on the surface of the charged conductor. Okay, the electric potential is constant, remains the same, where inside and on the surface. So here it is V is equal to Vs. The charges are resides on the surface. We know that inside there are no charges and no electric field, but the potential inside and what the potential we get at the surface, both are equal. Okay, so this is because electric field inside the conductor is 0. Therefore, there is no potential difference between any 2 points inside the conductor. Hence, electric potential is constant at a point inside and on the surface of the charged conductor. Now look at the fourth point. The electric field inside the cavity, you can see the cavity here, the space, empty space here, okay, of any charged conductor is 0. Okay, this is again a property we studied, that always the excess charge resides only at the outer surface of the conductor. Okay, so inside there are no charges. When there is no charge, no electric field. Therefore, the net charge and hence the electric field at any point inside the cavity is always 0. Okay, this is just a cavity, empty space. Okay, so inside the empty space of the cavity, the electric field is 0 and the charge is also 0. And the fifth property, at the surface of a charged conductor, electric field intensity must be normal to the surface. We studied in electric field line properties. The electric field lines which are coming out of the charged body is always normal to the surface of the body. Okay, that is the meaning here. Observe the fourth case once again. Okay, based on this we are going to define, okay, the electrostatic shielding. Okay, by using this concept, the phenomena, we can define the electrostatic shielding. Yeah, observe an interesting concept, electrostatic shielding. Shielding means something used to protect, right? Something we use to protect from external forces. It is the process in which the cavity of a conductor, cavity we observed in the fourth point, right? The cavity of a conductor is shielded from outside electric field. Process in which the cavity of a conductor shielded from outside electric field influences. This is called electrostatic shielding. Where we can use this shielding effect? The applications of shielding effects. The first one, it is used to protect sensitive components of electronic devices. Sensitive components. What are those sensitive components? Sensitive components like a galvanometer, voltmeter, ammeter, these are all very sensitive components only, and others, some other like electronic devices. Okay, it should not get disturbed from outside electrical influences. Okay, when there are multiples of wires and cables or get overlapped, the signals through the each wire should not get varied. Okay, it should not get affected with one another. To protect those sensitive components, we are using this shielding effect. And The second one, the shielding is used to design TV cables. We call it as a coaxial cables also. Okay, you observed in a TV cables and all, there is a central or the coaxial part, there is a conductor, over that there is a rubber material, over that there is a mesh kind structure, over that there is a complete insulated part, right? And this is how the TV cables or the coaxial cables made. Why they made like this? Because to avoid the external electric field influences, to protect the device or the signals from the external influence. The method we called as a shielding. And the third most one that is important here, you can easily understand this. Okay, now you will understand what is the actual meaning of shielding with this relevant daily related to example. It is in thunderstorm accompanied by lightning. Okay, it is safest to sit inside a car, right, or bus rather than near a tree or the open ground. Safest to sit inside a car. There is a scientific reason, because the metallic body of the car or bus becomes electrostatic shielding, right? Where you sit on the seats and all is a complete like cavity inside the car. It is we called as a cavity. The outside body of the car is completely made by the metal. Okay, so that protect us from the lightning has a enormous amount of electrical energies, right? From that we are get shielded, means we get protected if you sit inside the cavity, means inside the car. So all the charges get accumulated over the surface of the body of the car, because charge get distributed over the surface only. No charges will come inside the cavity, hence no electric field comes there. Okay, electric field is zero, charge is zero. If we sit inside the car, then we are safe. So this is we called as a electrostatic shielding. The next concept is dielectrics. Okay, dielectrics we also call it as an insulators, dielectric medium we studied, okay, while studying the Coulomb's force and the fields and all, right? The meaning of dielectrics is these are the insulator which transmit the electric effects. Okay, it transmits the electric effect without conducting the charges. It doesn't allow the charges to flow, but it allows the electrical effects to pass through it. Okay, the examples are mica sheets or the mica material, ceramics, pure water, oxygen, etc. These are all of good insulators we can call. Okay, in another name we call it as a dielectrics. In this dielectrics there are two types. One is a polar dielectric and one more is a non-polar dielectrics. What is the meaning of polar dielectric? These are the dielectrics made up of polar molecules. That polar molecules means these are the molecules in which centers of positive and negative charges do not coincide. Very very important here. Okay, centers of positive and negative charges do not coincide. You can see in a picture in the HCl, the H plus and the Cl minus. Okay, so both are separated with a certain distance, they do not coincide. And the polar molecules have unsymmetrical shapes. You can see in a picture. Okay, they have unsymmetrical shapes. So when they are separated with a particular distance, definitely they have a permanent dipole moment. Okay, they have permanent dipole moment. What is the meaning of dipole moment? P is equal to Q into 2A. There should be a distance at 2A. Okay, if they coincide, then there is no distance. If the positive and negative charges coincide, overlapped one on another, centers coincided, then distance becomes zero, then dipole moment becomes zero. But here in this case, charges, the centers do not coincide. Okay, there is some distance, right? Hence they have a permanent dipole moment. So these are the characteristics and properties of the polar dielectrics. The meaning of a polar dielectric is it is made up of polar molecule. These molecules whose centers of positive negative do not coincide, they are in unsymmetrical shape and they have a permanent dipole moment. Okay, remember these points, very very important. And examples for the polar dielectric materials are H2O, HCl, etc. Okay, so here the first diagram shows that positive and negative charges are separated with some distance, they do not coincide. Even in H2O also you can see there. Okay, there is an dipole moment. Now the next one is the non-polar dielectrics. It's just opposite to the polar dielectrics. Okay, these are made up of non-polar molecules like oxygen, nitrogen, hydrogen. Okay, the non-polar molecules have a symmetrical shapes. They have a symmetrical shapes. Okay, here they do not have a permanent dipoles. Okay, dipole moment will not come here because these are the molecules in which centers of positive and negative charges coincide. Okay, here it coincides, but in the previous case it never coincided. You can see in a picture, the first picture, plus or minus kind it is, you can see. Okay, that means positive and negative charges get coincided. Okay, and it is in symmetrical shape. Hence, there is no distance between the positive and negative charges. Hence, there is no dipole moment. So, such kind of polar molecules are the polar dielectrics we called as a non-polar dielectrics. Okay, this is an example, H2. So, both are coincided. In the figures appear to be a different, but it's actually coincided. The centers are coincided. Yeah, based on the dielectric concepts, we study the electric polarization. The meaning of electric polarization is the dipole moment developed per unit volume of the dielectric when we place the dielectric material in an external electric field. We call it as an electric polarization or polarization density. Okay, I'll repeat once again. Electric polarization means it is a dipole moment developed per unit volume of the dielectric. Okay, can see the dielectric material here. I am taking here the polar dielectric. Okay, for the polar dielectric, the positive and negative charges are separated with particular distance. You can see in the picture, right? So when you place this dielectric inside an external electric field, observe here, I kept a plates. One is a positively charged plate, another is a negatively charged plate. Okay, in between those two plates I kept the dielectric. Initially you can observe here there is a random orientation in a molecules. Okay, the molecules are randomly oriented, so the net dipole moment becomes 0. Means when you are not placed in a external field, before you place to external field, all the molecules, polar molecules are in randomly oriented and dipole moment is 0. When you take this material and kept in a electric field, external electric field, okay, you can observe the change here. The dipole moment is developed. Okay, when external field is applied, the dipoles align along the field direction. Observe the field direction, right, from positive charge to negative charge. The dipole moment also it get aligned like that. Negative charge to positive charge is the direction of dipole moment. We know this, right? The dipole moment direction is negative to positive. So here for all the positive charge plate, for all the positive charges on the plate, the negative charges get attracted. You can see the negative charges towards the left side. And for the negative charges, all the positive charges of the molecules get attracted, so it gets separated at the right side. Okay, it get aligned like this. This phenomenon we call as a electric polarization. Okay, so the net dipole moment developed in a polar dielectric when placed in an external field. Here is a dipole moment, but here there is no dipole moment. The same changes we can also observe in non-polar dielectric material. Observe in the case of non-polar dielectric material, non-polar means positive and negative charges coincided. Okay, it looked like a plus or minus. Here they are not separated, right? Here also net dipole moment is 0. For a non-polar molecules, the net dipole moment is 0. We know this fact. And when you place this dielectric material inside an external field, okay, there is a positive charge plate and negative charge plate, and because of these two, there is an external field directed from positive to negative. I am placing this dielectric material here. When I place this, you can observe here these positive and negative charges get separated. Okay, for the positive charge plate, all the negative charges are attracted. For the negative charged plate, all the positive charges get attracted, so they got separated. Now it's not looking like this, right? Observe the molecule is look like a plus or minus, but here it's look like separated. Okay, so we call this one as a electric polarization. This electric polarization we can also we can study, we can observe even for a polar dielectric material and even for a non-polar dielectric material. Okay, here the dipole moment get developed in the direction of the external field. So related to this, we can also study that dielectric breakdown, dielectric strength. Okay, those things we can study. And this electric polarization or the polarization density, what we call, is a vector quantity because it is having a direction, right? The dipole moment, how it is developed, it is having a direction, it is in the direction of external field. So this electric polarization is a vector quantity. Okay, and its direction is always in the direction of external field. And related to this dielectric material, I can give one more definition, that dielectric strength. It is the maximum value of electric field strength of applied field up to which dielectric breakdown doesn't takes place. Okay, up to which dielectric breakdown doesn't takes place. This is the definition of dielectric strength of that particular material. Every material has its own strength to withstand with the external influence of electric field. Okay, we know that the dielectric materials, the mica sheet, ceramic, pure water, oxygen, nitrogen, hydrogen, all are dielectrics only. Okay, but each and every dielectric molecules has its own value to withstand the outside electric field influence. So that strength we call as a dielectric strength. I'll repeat once again, the dielectric strength. Okay, it is the maximum value of electric field strength of applied field up to which the dielectric breakdown doesn't takes place. Dielectric breakdown doesn't takes place. Okay, the meaning of dielectric breakdown, I can tell you like this: when a dielectric is placed in an electric field of very high strength, the electrons are detaches from their parent atoms and becomes free. Okay, then the dielectric behaves like a conductor. This phenomena is called dielectric breakdown. I'll repeat once again the meaning of dielectric breakdown. When a dielectric is placed in an electric field like this of very high strength, this field strength, just imagine it is very high. The electrons are detaches from their parent atoms. Here in the dielectric material, electrons are those are detached from the parent atoms and it becomes free. Then the dielectric behaves like a conductor because once it gets the free electrons are free to move, right? Then the dielectric behaves like a conductor. So that particular point where the insulator is going to change as a conductor, that we call as a breakdown point or dielectric breakdown. Okay, I hope you understood the meanings of dielectric strength and dielectric breakdown. Yeah, thank you.